Hello and welcome everybody to day 18 of Advent of Code. We're still a day behind. I have unfortunately been a little bit under the weather, so I've been not really able to spend a lot of time on this. I've been working a bit slowly. But I managed to get day 18 finished. Gonna have a look at day 19 in a while, see if I can make any sense of it. But day 18 was kind of a fun problem, sort of a kind of a 3D graphics problem, which are always interesting, but it wasn't a super complicated one. So yeah, let's just jump straight in. It was kind of fun to solve, wasn't super difficult. Day 18, boiling boulders. So you've managed to escape the volcano with the elephants, but now you're seeing that there's still some rocks being thrown near your direction, and you realize that it might be forming obsidian glass. So you have these big rocks coming at you. You scan them as you go past, and effectively what happens is your scanner is not very good at doing it, so it ends up giving you this set of points which are XYZ coordinates, and each of those XYZ coordinates corresponds to a cube of dimension 1 by 1 by 1. So effectively you've got this 3D grid which represents your rock or your piece of obsidian glass, and each point is a little cube, and that's how we know the shape of our cube, or the shape of our thing that we're trying to work on. So we're interested in, like, I think how long it'll take to cool down or whatever. So what you want to do is you want to figure out the surface area of this droplet that has fallen. So that is a relatively simple problem. We've got a whole bunch of cubes, and the cubes are sort of stuck together based on their coordinate system. So if you were to look at it in just like a flat plane, you'd basically have, like, two cubes stuck together here. So this surface of both of them that's stuck together is invisible, so it forms a larger rectangle shape. The surface area of that in its units, because they're 1 by 1 by 1 cubes, the surface area of that would then be 10. So effectively, we need to apply that same idea of our two cubes that are adjacent to each other. They share a face, which is now not exposed as surface area. So you need to apply that to all of your coordinates that you have, figure out which are adjacent to each other, and then calculate the amount of faces that are exposed fully or not exposed. So a cube has 6 faces. So if you have a cube that is not adjacent to any other cube, and this is also adjacent by the faces, so the diagonals don't count in this case. And so what you're trying to work out is how many faces are exposed on the cube. So again, like I said, if you have a cube in free space, it has 6 exposed faces. So what you're trying to do is you're going to work out all your coordinates and calculate where there's faces that are touching, and then subtract that from a total number of faces that you would have. All right, so let's go. Okay, part 1. I start off here. I basically create a map of all my cubes. So I use like an XYZ coordinate hash, and then I store each of the XYZ coordinates, and I store a counter for basically the number of exposed faces that cube has. If it's, again, I said, if it's a cube in free space, it has 6 exposed faces. Otherwise, it'll have some number between 0 and 5. 0 being the case where it's a cube that's completely surrounded on all sides. So if you could imagine sort of like a diamond-shaped 3D thing, you basically, the middle section of that would have 0 because it's completely encased in the other ones all around it. So the way we calculate this, or the way we figure this out, it's really simple. It's only 30-something odd lines of code here. Basically what I do is I go through every single cube that I have. I take that cube, I pull out its XYZ coordinates, and then effectively, so I've called this faces here, it's actually really adjacencies to it, but they sort of represent each face going outwards by 1. So if you've got 6 faces, you've got your XYZ coordinates for this one. 2 of those faces would be adjacent to X and Y, and then Z plus 1 and Z minus 1, and then the same all the way through. And you can see I have those listed out here. So again, this is a set of all the adjacencies that you have. And to determine if a cube's face is unique, or if its adjacency is empty, basically, which would mean it's exposed, all you have to do is you have to just look at the coordinates set for that and see, does that exist in our master list of cubes? If it does exist in our master list of cubes, we'll do nothing. If it doesn't exist, we'll say it's an exposed face or an exposed cube of air, basically. And we'll calculate the size of that, and then we stick that in back into our hash up here. We update this value with the number of exposed faces, and then at the very end we just collect them all together in a sum. That's it, simple as that. And it runs pretty fast. Yeah, so 0.03 seconds, pretty quick, and that gives me the right answer. So part 2 then, on the face of it, they don't seem to, they're not asking you something super complicated, but then I kind of tied myself in knots with this, and I didn't know a really good approach to figure out had I done this the right way or not. Now, there are some approaches. I did look up after the fact. I looked up some other people's approaches, and there's some algorithms you can use. There's one called FloodFill, which a lot of people are able to use, and a lot of people use some other clever, what are they called? Clever sort of searching algorithms and stuff to try and work this part out. I thought there'd sort of be an analytical Matsy type solution that I could apply to it, and that it would work, and I'm sure there probably is, but I couldn't work it out in my head, and I wasted a bunch of time when I could have done a more brute force version and just had it done quicker. So anyway, what we're told here is, we're told that there's like air pockets inside your droplet, your lava thing, and what we're trying to find is, we're trying to find just the external surface area now. So if you imagine previously we had, so we say if we had our shape was actually sort of a boulder kind of shape, the middle of it might be hollow, and the outside obviously then there's like a crust. And what we calculated previously by just looking at the adjacencies, we were including in surface area the internal void, because the cubes that map to the, like, so if this is the surface of my thing, I have all these outside, so these are obviously exposed surfaces, but on the inside here, these are all also exposed surfaces based on the adjacency rules. So our same logic doesn't quite apply, but there is something relatively simple we can do to actually determine whether something is inside or outside of our overall shape. So let's have a look at how I did that. Part 2. So the setup, it starts the same. I basically read in my file. I work out almost the same data structure here. So I do my loop, and I determine what are my like exposed faces, which I store here in an array, the exact same as I did before. I even also have the count still done, even though you don't need it. So the next step now is, I know what my list of my exposed faces are. So now I need to determine whether one of those exposed faces is on the outside or the inside of this, closed surface. And we can do that pretty easily. Well, it took me a little bit of a mental leap, but I got there. So what I've decided to do was, I picked sort of an arbitrary point outside the sphere. So if this is our sphere in 3-dimensional space, the coordinate space we're given is pretty small. It's like, between 5 and about 40 or so. So it's a pretty small box that we're given. So if that's here, I basically set a point at like 0, 0, or the origin more or less, and say, okay, if I'm at any point on this exterior, can I walk my way one step at a time to get to the origin? or the other case is, if I'm inside the rock, so I'm somewhere in the hollow of the rock, I won't be able to get to the origin. No matter how many steps I take, I can never get there. I'll either hit a surface point that is already part of my rock, or I'll just cycle around inside forever and never actually be able to leave the rock to never get to the origin. So I've done that here. I basically have this walk method. So I go through each of my external points, and I go through this walk method, and that down here is just a simple recursion that I go through. And with that recursion, it basically exits true if I manage to escape my bounds, which I have set 2 bounds. I have an upper bound and a lower bound. One is basically going to 0, and the other one is going outside of about 40, which for my inputs that worked. Aside from that, you can also do it so if you end up recursing through your entire depth and you've not managed to escape, if you end up in just a loop that's going for about, because if you just leave this running, there's cycles that will never, because there doesn't have to be, there's cycles that will never leave the actual bounds. But if you've managed to just wander around for like 2,000 steps and not hit a wall and not hit something, then I've assumed, okay, you're probably, you're probably safe to say that you're an outside point, because if you're inside, you would have eventually hit a wall, or you would have tried to visit every single point already, and then you just wouldn't be able to go any further, which is another case I have in here. So I maintain a list of all of the coordinates that I visited, and that's pretty much it. For me, I had to set an arbitrary recursion depth to make this work properly. I trial and error set it to about 2,000, and it worked. So I sort of just continually increased it until the values I was getting out didn't change anymore, and then I brought it back down again to sort of the fastest level that I could make it run at. And it's not very fast. It's actually brutally slow, unfortunately. I think it takes about 15 to 16 seconds to actually execute, which is not ideal. But it does work. It gets me in the answer in the end. There's probably some optimizations I can do here to speed this up. I was thinking about my search space and I was thinking about ways to get that better, so that's just finished. It took 18 seconds, but it gave me the answer. So yeah, I'm happy enough with that. It works. It kind of required a little bit of gymnastics for me to work out that would work. Well, it's sort of like I knew how to do it. I knew what the crux of solving the second part was. I just couldn't think of what tools I should use to do this. So settled on this in the end. It's kind of a dirty method, but it worked. So yeah, I don't have a huge amount more to say about that. I'm going to go and have a look at number 19, day 19, and see if I feel a bit better. And yeah, hopefully I'll be back with another video. I don't know how long these are going to take now. I don't know how long these problems are going to take. We're in the very back half of this, and I'm definitely slowing down a bit. So anyway, thanks for watching, guys. I hope you enjoyed. I hope you're enjoying following this odyssey of mine to try and do this before Christmas. But, we'll keep going as long as we can. And yeah, I'll see you guys maybe tomorrow. Who knows? Bye-bye.